If you've been looking at the news, a brand new video generation model's come out called Sora 2, and it is crazy, right? I've been predicting that, in these videos that something's going to come out that's so photorealistic, and Sora 2 has come out. But what really sort of struck me when I saw it is the fact that they offer this ability to clone yourself in AI. So what you do is you can take a video of yourself talking, saying some words, and then it's able to project yourself into these AI videos. And it got me thinking, how might they do that? And one of the ways they might be able to do it is by using something called low-rank adaptation, which I want to talk about today.
Do I remember LoRA? Is that something to do with MikeBot?
MikeBot 3000, yes, we're going back to that video.
Hi everyone, I am MikeBot.
Well, in that video, we tried to recreate Mike Pound in AI. The LoRA was very much the linchpin of the whole thing. It was how we were able to generate new content of Mike from the diffusion model, right? So we've gone over how diffusion works. I'm not going to go over that in detail today, but the problem with these diffusion models is that you or I are not part of the training set. So, unless you're famous, right? So you can make videos of like Donald Trump or, Elon Musk or whatever, because they're in the training set. But you or I cannot, you cannot generate new content of us. So what you have to do is retrain a neural network to learn who you are. So let's say I want a new image of Michael Pound. So you can give it a token, Michael Pound, for example, and you pass it into the neural network, and it will spit out a man with a giant afro. That's not Michael Pound, right? And the reason for that is because the neural network doesn't know what Michael Pound is. So it hears Michael Pound and thinks it's just some guy and generates an image of that. So what we want is to generate new content of Michael Pound. So if we go into a layer of these of a neural network, right? What it really is just a big matrix of weights. It'll be much bigger than that. It's not going to be 4 by 4. It'll be like 1,000 by 1,000 or something like that. But it's basically a bunch of values here, right? And so what we want to do is change these values to encode what Michael Pound looks like. So how you can do that? Well, there's different ways of retraining a neural network. So the first one is you just retrain the whole thing, alter these weights to encode Michael Pound. But the issue is that your GPU will explode because these networks are absolutely massive and it's not going to happen. Another way you could do it is by adding in extra layers here. But that's how you start getting into things like control nets, which are different topic altogether. But what we really want is to change these weights by adding a small amount of differences here that will, when you put that input in, it won't generate that, it will generate a nice image of yourself or Michael Pound. Ooh, that's my attempt at drawing Mike.
Is that Mike's haircut?
That is really bad, isn't it? But you get the point, right? So the issue that I'll put this over here. The issue that these researchers found is that these matrices, if you're going to have a matrix that's the same size as the matrix of the weights, it's very large. And what will happen is that when you're retraining it, it'll be very slow. It won't work, right? And the fact that you're just trying to add Michael Pound in, you don't need all of this information. It's a lot of information for one concept. So what they realize is that these big matrices here can actually be represented by two low-rank matrices instead. Rather than having that, you can actually represent a matrix as two low-rank matrices that when you multiply them together, produce the very large matrix there. And so the rank of these matrices are actually just this part here. And as long as the height and width are the same as this, then you're okay. It doesn't actually matter how large these are, right? And so essentially you can reduce the number of dimensions here to be quite small, meaning that when you're retraining a neural network in this sort of format, what you do is you will just freeze these values so they don't change. And these values will encode things like how to draw a fish, how to draw Saturn, and all those concepts of how to draw things. What these weights will then will then focus on is how do you generate a Michael pound. But you don't want to override these weights because that's how you draw things. That's how you get new content. What these weights are doing is just altering these slightly so that then you can generate what Michael pound looks like. So what I'll do is I'll give you an example of how those matrices can multiply together. So I've drawn a matrix that will represent a LoRA for one of the layers in a network. And let's say this matrix here with these values is critical for drawing Mike's nose, for example, right? You can actually represent this matrix as two low-rank matrices. If we go through how the matrix multiplication works, to get that value of 1, you could times 1 by 1 to get 1, 1 by 2 to get 2, 1 by 3 to get 3, so on, so on, so on. But what's really important and cool about this is that suddenly you're representing this matrix as two smaller matrices here with a rank of 1.
So the rank there is just that one dimension is only 1.
Only 1, yeah. And the thing is with these neural networks is that the layers and these matrices will be like 1,000 by 1,000, right? But suddenly you're able to represent them by these two matrices will be, let's say, a rank of 8 by 1,000 by 8 by 1,000, which is so much smaller than 1,000 by 1,000, right? But you may be going, okay, that's fine for this matrix, right? But what happens if we want to change this value to 4, for example? Okay, well, what we can do here is we can change that 1 to a 2, because 2 times 2 is 4. Oh, but suddenly that 1 then becomes 2, and that 3 then becomes 6. Okay, what if you change this to 4 and that to 1? Well, that then becomes, 4 by 8, and that then becomes 12, right? And suddenly you're changing too much of your matrix there. But so what you can do to counter that is to increase the rank, right?
So that's the dimension we just said is 1.
Yes, exactly. So now if we redraw this, now I'm going to do this, so just give me a second here. Okay, so I've redrawn this now, but with a rank of 2, right? So suddenly these dimensions have gone from 1 to 2. And suddenly you're able to add all these values in there that give you much more flexibility of what these values can be. So suddenly, if we're going to change that to a 4 rather than a 2, we can add this extra dimension here, because when you do this calculation, 1 times 1 is 1, 1 times 0 is 0, plus add them together, you get 1. But you get to here, 1 times 2 is 2, 1 times 2 is 2, add them together, you get 4. But because the rest of these are 0, none of these other values are changed, right? So by increasing the rank, you get to increase the flexibility of the matrix that you then produce by timesing these together. And so basically the question comes down to how big do you want that rank to be? Because the larger the rank you get, the more of these different values you can get and represent. But the larger you make it, suddenly it starts to become larger or as big as the matrix you're trying to multiply together to get. Because suddenly, if you look at this example, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 values representing 9. So actually, it's not very efficient, it's actually worse. But in reality, as I say, these will be 1,000 by 1,000. So if you increase the rank from, let's say you need to increase the rank from 8 to 16, it's actually not that much of a difference, right? And that's enough to represent these large values. And you may be going, hang on, how is that the case? Because you've got thousands and thousands of values in these large neural networks being represented by these few values that when they times together, you don't actually have a lot of flexibility over what you can produce. And what they found was this phenomenon that a small change can make a big difference, which I think is quite nice.
So is there compromise sometimes in these? Because it reminds me a little bit of the JPEG discrete cosine, where it's kind of tiny little things are making, but presumably sometimes it can't be perfect.
Yeah, it can't be perfect. But this is the thing, as I say, it's a trade-off between quality versus how much you want to retrain and how large these LoRA changes will be. But actually, interesting enough, they found that at a certain point, it doesn't actually make that much of a difference because these values will just be redundant, right? So now I've explained how you can retrain a neural network using these very small matrices. How would you go and end up cloning yourself, right? Well, actually, you don't need that much input data for training these things. We've explained in the MicBot video, but you only need about 20 images of yourself and a caption to then be able to figure out what these weights are in order to generate more content of yourself. By having these low rank matrices generating this matrix here, you keep all of these weights here. That will encode, how to draw someone, how to draw different things, and we went over this in the MicBot video, but because these are all scalar values here, you can scale these by a certain weighting factor, which will determine how much impact this LoRA has on the neural network. And so by increasing it, you will inject more of the concept you want into there.
More Mike.
More Mike in there, yes, more Mike. I think we've got an example of Mike as Michael Zalski on there. Maybe you could show how increasing it injects more Mike into there. But at a certain point, what happens is that these values become so large and so overpowering that suddenly you lose the concepts that you've got in this original matrix here, and then suddenly it will forget how to draw anything, and it just becomes noise. Benefits of using these low-rank matrices here, rather than retraining the whole thing. It's quick. You won't break your GPU because you're only training a small amount of these versus a massive matrix here for the layers. And what you can do is that if you want to have multiple LoRAs, you can just add these matrices together. And so you can have Mike Pound shaking hands with me, because I may have a LoRA of myself, right? And I can create me and Mike in,
a multi-pack.
A multi-pack, yeah, exactly. However, what I will say from my experience of using these is that the more you add, the more sort of the loss, start getting more loss in quality, right? Because as these weights merge together, they may lose.
Your mileage may vary.
Exactly, yeah. So that's another thing you can do is combine these together. And sort of adding these new, there's sort of so many applications of these LoRAs, because you can use it for injecting yourself, new concepts into images. I use it a lot for things like synthetic data, making things look real. And this doesn't have to be for images as well. You can do it for videos, you can do it for LLMs. So essentially, all this boils down to is a way of retraining a neural network using low-rank matrices that make everything faster, reduce the storage, and make it more efficient. I just found this really impressive because it proves the theory that you can change the outcome of a neural network just by changing a few of the weights in here. And this is essentially a way of just figuring out what small changes you need to make to get the desired outcome. So the take-home message is that bigger isn't always better. You can get the job done by just by changing a few weights here and there.
Hawaii is a series of islands. They couldn't just run cables everywhere, and so they decided that they would build a wireless network. In 1968. They had two radio frequencies that they'd use. They used one to transmit from the IBM computer out across all the islands of Hawaii, and then they had another radio